Okay, check your email. There's a statement about a question on the exam. Some of you have noted that there is, I'll even tell you, question number 5 where the same answer appears twice. The dumb thing is I was really trying to revise that question, and I even remade all of the figures, and in rearranging things and copying and pasting, I did it again. So, yeah, sorry about that. With that question, simply select an answer that you feel is correct. The key has been adjusted so that any duplication should not affect anybody's grade. All right. So, if you already took it yesterday, should your score already be adjusted? Yes. This is why we like multiple choice exams, because I can click things and adjust the key, and then everybody's test is regraded. So, all right, any other questions, issues, complaints, suggestions? No, okay. All right. So when we were talking last, we were getting to the point where we wanted to bring everything together and then start answering sort of predict products questions about all the substitution and elimination reactions that can occur. And I'll take you through what I feel is a useful way to think about things, a couple different useful ways, and then we're going to work on some practice problems. So as we've talked about substitution and elimination reactions, there are two main factors to consider, right? You have the influence of the nucleophile, and then you have the structure of the molecule that has the leaving group. In this case, we'll call it the alkyl halide. And you've got primary, secondary, and tertiary. And then you've got things that are good nucleophiles and good bases. You have things that are good nucleophiles but weak bases. You have the small class of molecules that are good bases but weak nucleophiles. And then you have, and that's because of sterics. So you're thinking about butoxide, DBU, DBN, and so on. And then you have the weak nucleophiles that are also weak bases. This is basically water, alcohols. That's great penmanship. I guess I know where my son gets it, right? When I was in, was it second grade? In a little town called Paris, Texas, we were being judged on our handwriting. And I got a C, and I remember my dad coming out in the backyard to talk to me about how I could do better than that. So sometimes I've considered that to be an inspirational experience that helped me, but I'm wondering now in retrospect whether that might explain a lot of my issues. All right, anyway, sorry. So the principle here with our nucleophile situation is that good nucleophiles prefer substitution, good bases prefer elimination. When possible, neither of them wish to wait around for the leaving group to leave. And then for the alkyl halides, we remember that E2 is slow for primary alkyl halides, whereas SN2 is fast. And E2 is fast for tertiary alkyl halides, but SN2 doesn't happen for tertiary alkyl halides. So with all of this in mind, we've got sort of an intersecting set of 12 different situations that you can encounter. And we should be able to deal with each of them. Some of you like memorizing stuff, including charts. You're welcome to do this. I've had students wait till they get into the testing center and then write this down on their paper as quickly as they can so that they have it. I don't know that I recommend it, but that's a strategy. So a good nucleophile that is a good base with a primary alkyl halide You would think this category you want to be aware of the possibility for SN2 and E2, but for the primary alkyl halide, because SN2 is faster than E2, all you really need to worry about is SN2. All right? In contrast, for a secondary alkyl halide with something like, say, an alkoxide that's both a good nucleophile and a good base, you're going to worry about both of them, SN2 and E2 products. I will never ask you to tell me whether elimination or substitution products dominate. That's sort of a case by case. You've got to do the experiment and see. Among the elimination products, we've talked about briefly how the more substituted, more stable alkene is the favored product, and we'll say a little bit more about that later today. For the tertiary alkyl halide, because SN2 isn't possible, all you've got is E2. All right. Now, if you just have a good nucleophile that's not a good base, then that simplifies things considerably for the primary and secondary alkyl halides. For the tertiary alkyl halide, you're still stuck. Good nucleophile can't attack a tertiary alpha carbon because sterics. So you have to wait for the leaving group to leave, and at that point, you have the SN1 and E1 mechanisms. All right? And both those always compete, and I will never ask you to say whether elimination products dominate over substitution products. Among the elimination products, the more stable alkene should be the major elimination product, but I'm not going to ask you to make the distinction between substitution and elimination products. Now, this category is easy because it's just a really strong base that can't do substitution reactions and doesn't want to wait for the leaving group to leave, and E2 is possible for all of these, right? We said E2 is slow for primary alkyl halides, but if you use a sterically bulky base, what other choices do you have? So it's E2 all the way down here. And then lastly, if you have something that's a weak nucleophile and a weak base, nothing happens until the leaving group leaves, and then you get SN1 and E1. Though we've said that for primary alkyl halides, because primary carbocations are too unstable in solution, we'll say that nothing happens, but we're going to put an asterisk on nothing, and we're going to say, beware the allyl leaving group, or the possibility for the resonance stabilized carbocation. If your carbocation can be resonance stabilized, then SN1 and E1 are totally good possibilities, even if your leaving group is primary. Okay? Questions about that? Yes?
You say the allele leaving group, is the allele actually going to be here, just affecting this allele close to the
I mean this situation where if this is the vinyl carbon and this is the allyl carbon, this is an allyl leaving group. If it leaves, you get a resonance stabilized carbocation like this. Make sense? Yeah? Okay?
No.
Same thing? Okay. Anything else? All right. In the past, I've drawn a complicated energy diagram, which I realize was probably more about me liking to draw than it was about making sure students understood stuff. So I guess I won't do that today, but I do want to just gotta find, still not, yeah, this thing. This just, I think, illustrates the fact that all of these reactions compete with each other and can give you a sense for what factors change things. we start out here. This is the starting material. Here's our substitution products. Here's our elimination products. There are two paths to both substitution and elimination products. The one we've been considering most recently, though, is the one where the carbocation, where the leaving group leaves to give you a carbocationic intermediate. And at that point, you basically have similar rates of reaction towards substitution products versus elimination products. Let me talk about, again, some things, and this is going to reiterate what's in the chart, some things that can bias you to one pathway versus the other. As the substitution of your alkyl halide increases, the transition state energy for SN2 gets higher. That's because of sterics. It gets harder and harder to do the SN2 reaction because backside attack gets much more difficult for tertiary alkyl halides. As that SN2 transition state increases in energy, at the same time the transition state for leaving group leaving decreases in energy because tertiary carbocations are more stable, right? So you have a trade-off. If I were to plot where the transition states are for the SN2 reaction versus the leaving group leaving reaction, I might say what makes this transition state higher in energy as you get to a tertiary alkyl halide from a primary alkyl halide. And that's why we're going to have SN2 be imperceptibly slow for tertiary alkyl halides. In contrast, you're going to see that transition state energy gets lowest for the tertiary alkyl halide versus the primary alkyl halide. That's because of what we talked about for the Hammond postulate, which tells you that because this is an uphill in energy step, the transition state for the carbocation forming is very carbocation-like. So we use that principle up here in the chart where we say that SN2 is fast for primary alkyl halides but is slow for tertiary alkyl halides. So you get that sense for that trade-off, that these two possible transition states go like this depending upon the alkyl halide structure. Yeah?
I think I understand. And also, I just wanted to clarify too, the reason that the SN2 doesn't happen with the tertiary carbons is just because there's so much stuff in the way there.
Yep, there's just so much stuff in the way. We can illustrate that in Spartan. Here is a tertiary alkyl halide, and you can see where the sigma star is in relation to everything else. Some of the LUMO is on the beta protons, but if I show space filling, remember where the sigma star is. It's almost entirely blocked by those adjacent methyl groups. Yeah, so that's why the SN2 is not a good pathway for tertiary alkyl halides. All right, so for the E2 pathway, E2 is fastest, if we think about the E2 transition state, E2 is fastest for tertiary alkyl halides, though it's possible for all three. So in elimination reactions, what really biases you towards the leaving group leaving is when you don't have a good base at all, okay? Right. So should we do some examples at this point? You guys good on carbocation stability? Yeah, go ahead.
Could you explain what makes a good nucleophile again or a good base?
Sure. Yeah, so good nucleophiles.
Just nucleophile, not base.
Sure. Good nucleophiles generally have conjugate acids with pKa's that are greater than 0. If you look at our list, this is things that in many cases have negative charges, though not always. Whereas good bases, we're going to say have conjugate acids with pKa's that are like greater than or equal to 16. So we're thinking hydroxide, alkoxides, perhaps deprotonated alkynes. So yeah, there's just sort of a cutoff where you get reactive enough that removing protons is possible. Yeah.
Along those lines, I wanted to ask about like the acetate ion, because that one does fit like our definition of like a good nucleophile, but there's also kind of a lot going on.
Yeah, so the acetate anion like this, that's a good nucleophile, yeah. Yeah, probably not a good base because its pKa is not high enough. The conjugate acid pKa is not high enough. Okay, what else? Yeah.
Can we do a quick review of carbocation stability?
Quick review of carbocation stability, yep. Tertiary, more stable than secondary, more stable than primary, more stable than methyl. And reasons for that are hyperconjugation. Yeah?
Could you just really see what hyperconjugation would look like on the molecular model that we're showing for in the case of carbocation?
Could you see hyperconjugation here for a carbocation? Unfortunately, Spartan doesn't do carbocations. I can do the calculation. How much time do we have? Yeah, I mean, I don't know whether this will necessarily be useful to anybody, and it may take too long. I'll just quick set up the calculation. We can run it and then maybe see. And if you hate this, you can comment you can comment at the end of the semester about how egregiously I wasted class period time. No. So hydrogen. Boom. Setting up calculation. Let's do optimization, minimum, default, method, Hartree. Blah, blah, blah. Charge 1, carbocation. Oh, I was about to choose something that, dang it. You want to see hyperconjugation? What do you guys want? You want it to be tertiary, primary, secondary? What do you think? Tertiary, okay, bloop, bloop. Bring that back up. Gig for population. All right, we'll just tell it to go. Okay, we'll see if it even finishes during class time. Yeah, so I'll see about that. I could draw it for you, but if you want to actually see it, we can see it. Okay. What else? While we're at it and on the subject of hyperconjugation, we've mentioned that several times that that the E2 and E1 reactions tend to give the more stable alkene or olefin as products. So a couple of principles for alkene stability. Trans is more stable than cis because of sterics. And then tetrasubstituted is more stable than trisubstituted, which is more stable than disubstituted, which is more stable than monosubstituted, and so on. This language about alkene substitution. I understand that's confusing because we're using the word substitution in a different way. All of this is talking about the structure of the alkene relative to this unsubstituted alkene model compound. So if you have one non-hydrogen thing, it's monosubstituted. If you have 4 non-hydrogen things, it's tetrasubstituted. So that's alkene stability. We haven't talked about why, and I don't like to not talk about why, so we can. I'm just going to check and see whether, oh, we're done. That was fast. Oh, shoot. All right, it's going to try to think for a while and generate what the orbitals look like. All right, so we can talk just briefly about what makes alkenes more substituted, what makes more substituted alkenes more stable. I'll give you a hint. The answer is hyperconjugation. So it actually follows carbocation stability trends pretty well. Remember, the issue with carbocation stability is that the more adjacent beta protons you have, the more they can donate into the LUMO, which is the empty p orbital. Same thing is true for the alkenes. Let's just draw a monosubstituted alkene, and we'll draw it sort of laying on its side. We would say the LUMO of an alkene is the pi star, which we would draw like this. It would sort of look like 2 p orbitals, but with opposite wave function sign and a node between the 2 nuclei. That's an empty antibonding orbital, right? Pi star, empty. And on an adjacent atom, you have a carbon-hydrogen bonding orbital that can mix with the pi star in a way similar to how the sigma bonding orbital mixed with the empty p orbital above. Remember, we talked about hyperconjugation being mixing in the same molecule of an empty orbital with a filled orbital that allows the plus combination to go a little bit lower in energy and makes the minus combination a little bit higher in energy. I've drawn the minus combination here. But what this does is it spreads out these electrons, allowing them to move lower in energy, and that's a stabilizing thing. So we're going to see, for the same reason that carbocations are more stable when they're more substituted, so also alkenes are more stable when they're more substituted. Yeah?
Just making sure this is where these are not lined up, right? I think this is the last combination.
Which are not lined up, sorry?
As in this case, the orbitals aren't lining up so that hyperconjugation can occur.
They are lining up so that hyperconjugation can occur.
So there's opposite phase.
Why are they opposite phase? Yeah, this is the minus combination. You could have drawn the plus combination, yeah. All right, let's see if it's going to show us stuff. That's dumb. I think I made a mistake. We'll try again, maybe, or not. Charge plus singlet, yes. That's what we wanted. I want it to be restricted or default and submit. Yes. Yes. All right, we'll see. Sorry about that. Okay, so with all of that, we're now prepared for some example problems. So I'm going to take these, I think, mostly from your practice exam. Yeah, Jack hasn't done anything for us. That's too bad. All right. So yeah, rather than copy these down on the other notability, we'll just leave it. Okay. So. Oh, we're done. Okay, sorry. I realize this is an ongoing distraction. And okay, carbocation, it's flat. That's good. Because we're told carbocations are planar. Now I want to see the LUMO. Visualize, medium, number 2, go. Oh shoot, that didn't do anything, did it? Update. No, man, force quit. All right, back to practice.
Dr. Price, will we have to consider product solutions when considering reactions?
Okay, yeah, so the question is one about protic versus aprotic solvent. That is in your text, and I have neglected to talk about it because it doesn't really make a difference in terms of whether a reaction's SN1 or SN2 or E1 or E2. It is a subject that your actual practical organic chemist has to deal with. Protic solvents are solvents that contain protons with pKa's that can be removed by strong bases. So examples of and I'm not sure what the actual cutoff is, but basically it's solvents with relatively acidic protons. So water, let's see, an alcohol of some kind. Sometimes people use acetic acid as a solvent. And whereas aprotic solvents are solvents that don't have acidic protons. So hexane is one of them. Ethyl acetate is another. Dichloromethane is another. When you go to take the organic lab, you'll encounter these solvents. Some solvents are nonpolar. Other solvents like acetone or DMSO or dimethylformamide are polar but still don't have protic, don't have acidic protons. We'll see, and it's not such an issue here, your text talks about how depending on whether you use a polar aprotic solvent or a protic solvent, that can influence the relative nucleophilicity of fluorine, chlorine, bromine, and iodide. We're dealing with those as leaving groups in this chapter, and again, because it doesn't make much of a switch point, I'm just not worrying about it. Okay? Yeah? Right? So, tertiary alkyl halide, no SN2 is how I would think about this. Water is a weak nucleophile, that is a weak base, so no SN2 and no E2. So all you're left with is you got to wait for the leaving group to leave, and then you're going to get SN1 and E1. So the leaving group can indeed leave from a tertiary alkyl halide. So I would draw the carbocationic intermediate, planar and flat, at that positively charged carbon. Then I would show the nucleophile to give me substitution products. The nucleophile would attack, ooh, that's a neat arrow, pink. Nucleophile would attack either from above or below at that carbocation to give me a substitution product. I am not actually showing dashes or wedges here, even though I could. This is not a stereocenter, not 4 different things attached. I could show dashes and wedges to give you a sense for shape, but I'm assuming that you know what an sp3 hybridized carbon is, that it's tetrahedral. The fact that I'm not showing dashes and wedges means that there's no interesting stereochemistry there. If this were a stereocenter, using not dashes and wedges would, or rather not using dashes and wedges would communicate that you get both possible stereoisomers. The pKa of this proton on a positively charged oxygen should be around -2, so it is reasonable to think about water, which is probably present in a lot of excess because it's probably the solvent, can remove the proton to give you the neutral alcohol. Normally in organic chemistry we don't isolate charged species, we isolate their neutral counterparts just because of the practical aspects of synthesis. Now that's the substitution product. We have to deal with the elimination product. Let me just erase these solvents here, delete. Okay, so for the elimination product, we're looking for protons that are beta to the positive charge and can line up with it. I have two different identical, that's a funny thing to say. I have two identical protons that are beta to the positive charge. So actually I can just show one of the two doing the elimination reaction to give me the elimination product. Okay, questions? Yeah.
Why is it that you just show one? Because when they form a double bond, that's different.
So yes, I could have, if I had drawn the product from that other proton, it's exactly the same thing. It doesn't look like it is, but whoa. Pancake flip that and it's the same thing. Yep. All right. Let's just see whether this Gaussian program is, there we go. That's beautiful. Love it. Okay, so this is a carbocation, and that's the hyperconjugation. You're looking at the LUMO. The LUMO is mostly the p orbital on that carbon, but it's also on the adjacent beta protons that can line up with the empty p orbital. And you're looking at the minus combination. Yeah?
And the plus combination would have them kind of phasing into each other?
Yeah, the plus combination would look just like this, only the wave function sign would be opposite. In the middle, you would have it line up all in phase on top and all in phase on the bottom. Okay, yeah?
So just making sure we're looking at the MTP orbital and the carbon hydrogen sigma bond.
MTP orbital and the carbon hydrogen sigma bond, yep. Okay, all right, that's fun. I like that. All right, let's do some other more difficult problems. Let's see, what would be, what?
The hardest one.
The hardest one? Whoa, that stuff looks hard. Let's do an easier one first. How about here, secondary alkyl halide with, you have to learn not to be distracted by counter ions. This is equal to CH3O minus, that is the conjugate base of methanol, pKa 16. So this is a good nucleophile, that is a good base. I would be worried here about SN2 and E2. And for the secondary alkyl halide, we know that SN2 and E2 are both okay. So I need to show both products. I'm going to need some more space. Right, so the SN2 product would be, what's going on? If the nucleophile methoxide attacked the sigma star of the carbon-bromine bond to give me the substitution product. Now, I am drawing this with a switch in configuration. Is this a stereocenter? Okay, good. You better be able to see that that is not a stereocenter. Therefore, does it matter that I've drawn the product this way? No, it's the same thing either way. I've only done this to communicate that it was backside attack, but it would be totally fine for me to show the product like this or like this. I just, because there is no way you can tell that backside attack occurred. Yes?
Just making sure for the SN1, you said that if you have, if it's not a chiral molecule and you have a received picture, you can just do without any front or back wedge, and that would be the right answer as well.
If I mean that I get both possible configurations at a stereo center, then yes, I don't need to use dashes and wedges. In the examples we've seen so far, that's not even an issue because this is not a stereo center. Yep.
Would we have to use a plus minus sign or no?
No, because this is not a stereo center. There's no need for anything else.
If it is a stereo center, sorry. If it were.
Okay, I'm going to defer on that till we have an example where that's the case, if that's all right. Okay, so that's the substitution product. Then elimination product. Remember, I need to find protons that are anti or can be anti to the leaving group at the beta carbon. And so, got that here. Remove the proton, make the double bond, the leaving group leaves. There is another beta proton on the other side, but it's identical. I'd get the same product either way, so my work is done at that point. Yeah?
You just wrote your leaving group as,
Oh yeah, that's fun, isn't it? That's a terrible leaving group. Okay. Okay, that's better, thank you. All right, let's maybe, yes?
In the question description, it says identify when a molecule is major or minor. When do we do that? Is that only for elimination reactions?
Right, identifying which is major or minor is only among elimination products. So here, even though I've got a substitution and elimination product, I frankly don't know how to predict whether one's going to dominate over the other. Yeah. Okay, yes?
Are you suggesting that the conjugate acid of the O with the methyl on it is the CH3O? Is that what you're putting there?
The conjugate acid of this nucleophile is methanol, where I'm, yeah,
I was looking at a weird thing.
okay, no, that's fine. All right, sometimes organic chemists will use abbreviations, ME for methyl group, and I will do that too, and it's irritating, but you'll get used to it. Oh, okay. Okay, okay. Oh, yeah, I could see that, yeah. All right, sorry about that. Maybe we'll just do that. That's better, maybe. Okay, I want to do an example where there's some stereochemistry. This might do. Okay, you've got secondary alkyl halide, and you have a nucleophile that is a weak nucleophile and a weak base. That means there's no SN2 or E2. For secondary alkyl halides, we know that SN1 and E1 are okay. So we can propose leaving group leaves. Now, this is a boneheaded reaction to do because chiral starting materials are expensive. And in the first step of this reaction, we've gone from something that was chiral to something that is not. So we've just lost stereochemistry. When the nucleophile comes in to attack the positively charged carbon, it may do so from above or below. I am not going to draw both mechanisms. You can show the product of this reaction, and I'm also going to skip the subsequent proton transfer step because I showed it above. I can show the products like this. I have to show, because I've made a stereo center, I have to show both. There are multiple ways to communicate that I have talked about in the study guide and which are correct. You could draw the molecule this way, where you just draw one of the two stereoisomers. You use the plus minus. That's a holdover from the days of optical rotation, indicating you've got the enantiomer that rotates plus and the enantiomer that rotates minus in the same amounts. Alternatively, it is perfectly acceptable to draw that as the product, and that communicates you get both enantiomers. Now, the substitution products that you would get, you have to come back to the carbocation and identify beta protons. So without drawing the mechanism, the E1 products include this monosubstituted alkene, the trans disubstituted alkene, and the cis disubstituted alkene. If I had to pick a major product among the elimination ones, which would it be? The trans disubstituted, okay. Major elimination product. Notice I am not saying the major product because I don't know whether it's going to dominate over the substitution product. 31 is easy. Potassium is a counter ion. Cn minus is a good nucleophile. Just tell me quickly what the product should be. SN2, right? Cn replaces Br. Boom, right? Primary alkyl halide, you don't have to worry about E2 if you've got a good nucleophile. 32 is another example of a reaction that would be SN1/E1. 33 is a fun one, which we maybe should talk about briefly. Yikes, I've already solved it. We're going to delete all of my beautiful work. Right, so tertiary alkyl halide, and I notice it's also an allyl alkyl halide. That is, the leaving group is on an allyl carbon adjacent to a pi bond. So that means there's going to be the possibility for a resonance stabilized carbocationic intermediate. I have here a weak nucleophile that's a weak base. That rules out SN2 and E2. So all that can happen is the leaving group leaves. Again, this is a boneheaded reaction because I had a chiral starting material and I just lost my stereocenter, which is why people typically don't do SN1 and E1 reactions synthetically, especially not in molecules with stereocenters. This carbocation is resonance stabilized. Drawing the hydrogen that's implied but not shown. So I need to consider substitution products from both resonance structures. Remember what resonance means. These are not two separate carbocations. Rather, the positive charge is shared between those two carbons, right? So it's reasonable to expect that the nucleophile might attack one or the other. Would the nucleophile attack one preferentially in a slightly larger amount than the other? Possibly. I don't know. You don't have to predict that. You just have to anticipate both outcomes. The substitution products for this, for the first resonance structure, I'm again going to exercise my right to use not dashes and wedges when I want to communicate both possible stereoisomers. So this is one of my substitution products. If I represented that in any of the ways described above, that would be fine. My other substitution product is going to be this one. Right? Now with elimination products, I need to come back here and look for protons that are beta to the positive charge. I have one there. I have one here, which it turns out is never going to be a problem. And let's see, I have another one here on the methyl group. And then I have another one, we used orange yet? Here. Okay, why am I telling you not to worry about the green one? It's always out of the way, right? If you know what an allyl cation is, this 3-pi system that we talked about before, this proton is in the plane of the double bonds, it can never line up with the positive charge. It can never line up with the pi orbital that's represented by that positive charge on either of these atoms. So we're not going to show a product from there. Frankly, you don't have to remember that that's the case because I simply will not give that as an option on a multiple choice test. If we eliminate from the pink beta proton, we get the following structure. If we eliminate from the blue beta proton, we get this one, except that's kind of ugly. And if we eliminate from the orange beta proton, oh, wow, we should get this product. All right? Now, at this point, there's not a whole lot of difference in substitution of the alkenes between orange and pink. So I'm not even going to attempt to tell you which is the major one. You just anticipate there being a possibility of all of them. All right. Lastly, I want to take you through, whoa, obviously I've made this chart too many times. I want to take you through this example, which I think has been troubling to some of you. This is one of the only cases I can think of where a proton that is trans in a ring to a leaving group can't be anti to the leaving group. So this is a transfused decalin for reasons that we talked about before that are not terribly important, and if you don't believe me, you can make a model. It is not possible to make any other chair conformation of this molecule, okay? So with that in mind, as I draw the transfused system, I see that the bromo group is on an up carbon, and that bromo group is down equatorial, whereas the methyl group is up axial. Now, as I try to identify beta protons that are trans to the leaving group, I've got some of these, purple and blue, and they are indeed trans to the leaving group. They are up relative to the ring, whereas the bromo is down, but they're not anti to the leaving group. If you put your eyeball here and look down this bond, the leaving group is gauche to the proton instead of anti. So not able to line up with the sigma star, not able to really participate in the elimination reaction. Same thing with the purple proton. In fact, the only proton that can be anti to the leaving group here is the one on the methyl group, because you got free rotation around this carbon-carbon bond, and you can imagine a conformation where this bond is anti to this one, and that's the one we can do elimination from. DBU is a strong base, it's a poor nucleophile, so the only product we show is this one, and none of the other ones. If you miss that, if you draw the other options, you're communicating that you don't know that E2 requires anti-periplanar arrangement of the beta proton and the leaving group. All right, that's it. We'll see you Friday. Good luck.